All right, now we are in business. You can see my iPad screen, right? Yep. Yes. All right, so we're gonna finish the strong and weak form discussion. There isn't really that much more compared to last time. And because I'm not in the classroom, I'm not gonna make you do examples and pause and walk around. Just a little bit of a refresher of what we are doing and where this is going. These two lectures, the one on Monday and the one today, are kind of mathy, but there's a reason for them. They have a role to play in the overall FE formulation. And what we started with for the first week was this process, and just to get you to create this type of equation, this system of equations where you have some stiffness matrix, some displacements, and that equals some forces and reactions, and to give you strategies to do basically that assembly from element to global system. And then that was one of the things, and then to solve the linear system. So that's where we started. Now, that only applies for the system that is already discrete, like the trusses. And so when we want to do stress analysis, what we have is a PDE. And there is some massaging that needs to happen to go from the PDE to this system of equations. And in particular, what we were doing on Monday and what we're doing today is this part of the, how do you transform the PDE from this strong form to this so-called weak form, such that the weak form is what you can actually solve with finite elements. And then what we're gonna start next week is this approximation of functions. So next week, we're gonna go to actually defining finite element interpolations. That's what the topic is for next week. So recap of what we did on Monday, we had the strong form of elasticity in one dimension. And the strong form is basically your standard boundary value problem or PDE problem. You have a PDE, so some differential equation, in this case, the derivative, the second derivative of the displacement equals 0. This is essentially momentum balance or sum of forces equals 0. So this is basically sum of forces equals 0. But instead of sum of forces equals 0 works for rigid bodies. But if you want it to work for the entire body, then you have a differential equation. But differential equation. And so that you can see that that has to be satisfied over some domain, which I typically denote with omega. So you have to satisfy this differential equation over some domain at every single point of the domain. And then you have boundary conditions. So these are boundary conditions. And they can be of two types. They can either have a known value of the function that you want to find. So here, our known is this function u of x. That's what we want to find. We want to find the function u of x. And we can either have a condition on the value of the function. And so these are called several names. You can refer back to the Monday lecture, but these are called essential boundary conditions or Dirichlet boundary conditions. I think these are the ones that I use most of the time. They're also called displacement boundary conditions. And you can have information alternatively. If you don't know anything about the function, you know something about its derivative. And that's what you have in this other type of boundary condition. So if you know something about the derivative, these are called natural boundary conditions or Neumann boundary conditions, or traction boundary conditions. So I gave 4 names last time. I think the ones that I use most of the time are essential or Dirichlet and natural or Neumann. And again, the main distinction is whether you know something about the function or you know something about the derivative of the function at the boundary. So then I show you, maybe I'll recap it in a sec, or I'll do one extra example at the end to tell you how do we go from the strong form to the weak form. But assuming that you can go back and watch how I did that in the in the previous lecture, what you end up is you end up with a weak form which says find u, this is still the function u of x, so it's our same unknown. There's a little bit more math notation here. This is the more formal way of writing it, which is u is in some space of functions, and that space of functions is such that it's h1. I'm gonna talk about what this means. So this is what type of function we want u to be, and then I'll talk just a little bit more about that in a sec, with the essential boundary condition. So that one just says, what is my goal? My goal is to find the function u of x with just a couple of conditions. One is that it has to satisfy the essential boundary condition, and the other one is that it has to have certain degree of continuity. This just means u belongs to this H1 space or C0 space, which denotes some degree of continuity, and I'll define what that means in a sec, but it's just some little bit of a condition on that function u, such that this integral equation is 0, and this is after, integrating, multiplying by w, doing integration by parts, we ended up with this equation, and you can see that that equation has some integrals over omega, and this is basically an integral over the partial omega. So this is a boundary integral. It's just that in 1D, in 1D, a boundary integral just means evaluate at the boundary, because there's just 2 points in the boundary. For 1D, just evaluate at boundary points. So that equation, this equation right here, has to be satisfied for any W function, with the only condition that this W function satisfies that whenever there's essential boundary condition, the W vanishes. So W vanishes whenever there are essential boundary conditions. And again, some question about the type of functions. That's what we came up with. And it looks pretty abstract, but I'm gonna try to give you a little bit of intuition of what does this mean? What is this equivalent to, is this weak form equivalent to the strong form? Or how can we make sense of it? If I tell you to solve this equation, this kind of makes sense from your PDE class. You have some PDE that you want to solve. It represents some sort of equilibrium condition, like sum of forces equals 0. And then you have some boundary conditions. You either know a displacement or you know a force. So I think based on your previous classes and just basic knowledge of PDEs, this kind of makes sense, right? And it makes sense for stress analysis, for heat transfer, and as I mentioned in the very first introductory lecture, for a bunch of physics, electromagnetism, transport, and so on. But this one looks pretty weird, right? And so are these two really equivalent? And so that's what I'm going to try to show you, just to give you a little bit more intuition. So it's not just, this is the formulation and that's it, but what does this mean? And what you should think of this is sort of a way of calculating average errors. So if you think of the original PDE is, I'm just gonna take the AE outside of the, not U squared, just U. Something like this, plus B equals 0, 0 less than X, less than L. This was the original PDE, right? So this has to be satisfied for every X. So for every X, the function U has to be such that, let me just remember where I had the, This is the function u that I'm after. And that function u has to satisfy every point, it has to satisfy this equation. So this equation, which like I said, is sort of sum of forces equals 0, satisfies for every x. So for every single point here, that should be the case. And the boundary conditions, for example, here, this is one of our boundary conditions, right? That we know the value of the displacement at x equals L. Let's say that this is x equals L. That one we know, for example, let's say that it's 0. So we know something about the function in that place. And the other boundary condition, this is kind of a bad color. Yeah, change the color. So this is one boundary condition. And the other boundary condition is not related to the value of u, but something related to the value of the tangent, which is equivalent to knowing the force. So here, the derivative, which is the same as the traction or force, we know, which is, like I said, related to the derivative, is known at this other point. So this is our original problem, and the u is the displacement field would have some sort of function like that. Now, what the weak form does is, let's not worry about satisfying the solution at every point, but instead, let's try to get the average error by in some area. So this W function that I'm going to draw here, let's say that this is some W function. Let's just pick W1. Let's call it W1 of x. So if I multiply this W function by this U function, multiply U, well, not U, but multiply the PDE by W1. Essentially what I'm doing is sort of forgetting about the rest and zooming into some region of x. So I have x, and I have the value of the PDE times, let's just call it PDE times W. Now that one will look something, I'm just going to use a different color, but it will be 0 when W is 0 and non-zero when W is non-zero. So non-zero only when W of x is non-zero. Otherwise, it is 0. And so what we did, we basically forgot about things that happen outside of that W, and we are kind of zooming in to this region right here. And the key thing is that we are zooming in a region, not a specific point. That all depends on how wide that W is. But in principle, if the W is not super sharp, then you're zooming in a region. That's one thing that we're doing. And then the next thing that we're doing is we are integrating. So that's what we're doing when we were initially the first step of the weak form, which was multiply the PDE by W and integrate. You're integrating over omega, but in reality, you're really only integrating over the region where W is non-zero. So this is that's the meaning of that first step of the of the going from the strong form to the weak form. So what this is doing is essentially calculating an average error over region defined by W. So there's two key things here. One is that instead of looking at a error at every single X, what we're doing is we're using the W to get rid of some region, but not quite zooming into a single point, and then zooming into a smaller region, and then integrating to get an average error over that region. Then doing the integration by parts, that doesn't change anything. Integration by parts, they're just equal signs on the left and right. Is just a way to manipulating the integral. But it doesn't really change the fact that we want to do is we want to calculate some average error over W. And that's the main idea. So this is also called weighted residual or weighted error form. Weighted residual or weighted error. That's what this multiply by W and take an integral means. And again, what you did is you replace this error for a single point. So do I satisfy the PDE for every single point, or do I satisfy approximately over some region W? And so then the question is, when are these two? This looks a little bit messy, but so the question is, are those two equivalent? Is the original PDE equal to this weighted residual? And the answer is yes, but if you pick many W's and you make them narrower and narrower. So to illustrate that, again, the original PDE was this equals 0 for every point X in the interval 0 to 1. Well, actually, without including the edges, that was the original. And then instead of that, I'm gonna say, rather than doing that for every single point, which there are infinitely many of them, infinite number of points. When are these equivalent? Well, if I pick the integral and I pick also many W's and I make them sharper and sharper. So I have the same PDE. And every time I multiply by a W, I'm calculating an average error given by that W. And then I just need to do that many, many times. With different W's. And every time I do it, I'm calculating an average error of some region. So if the W, going back to my notation, so let's say that W1 is something like that. Let's say that my W2 is maybe a little bit more to the right, and my W3 is a little bit more to the right. So this is W2, this is W3. So you can see that when I multiply by W and I integrate, basically what I'm calculating is I'm calculating the average error over these regions. I'll look to the chat in one sec. So if I pick infinite number of W's and I make them sharper, then these two are equivalent because this weighted residual form is calculating an average error. But if I make these W's be sharper and sharper, then I'm calculating essentially zooming in into smaller and smaller regions. And then obviously I need more and more W's to be able to cover the space. So they are the same. It's just one says satisfy for every single point X. The other one says, let me use this W to sort of zoom in a little bit. And with the W, I can control sort of how much do I want to zoom in. And then if I zoom in a lot, then I can use many, many W's. And then they are the same problem. And now let me look at the chat. What's the error with context? The error is the PDE. So the error is whether or not I satisfy the, I don't know, cross that. The error is this. So whether or not I satisfy my equilibrium equation. So error is whether or not this is satisfied. Equilibrium is satisfied. And you can see the same. This is sort of your error is how far away you are from satisfying this. Do you sum these ratios to get a perfect match to the original PD? You don't sum them, you do all of them. And this is exactly what we are gonna do with the FE. So when we do the FE, what we do is we pick, now hopefully you will see what we will do with FE. So when we do FE, what we are doing is every element has a W in a way. So what we're doing is approximating the solution. So FE, and this is where FE comes into play, is that we're gonna create these W functions. We will split the domain into regions with associated W. And so every W will give us one equation, basically. Because, yes, so every choice of W will give you, if you think of the X line, and now let's say that you, and this is what the FE approximation will do, that we're gonna now split, and then we're gonna have multiple W's. And basically, it's actually W per node, not per element. So to every node, there's gonna be an associated W. And the reason why it's per node and not per element is because it's kind of like the truss, sorry, you need to tie them together. So you will have, yeah, for every node, you will have basically one weight function per node. And then when you do this integral, every one of these integrals will give you a row in the system of equations, because you are calculating sort of an average error per node. So we're basically calculating average error per node. And what you'll see is that each one of these W's will correspond to a line in our big K matrix. For each one of these, there's gonna be a line in the stiffness matrix. So every W gives us one equation. And you can see, again, if you choose, and this is sort of the intuitive part of FE, right? So if you split your domain into more and more and more elements, what you're doing is you're basically making these W functions finer and finer and finer and finer. And in the limit, if you pick infinitely many nodes, essentially what you're doing is you are doing this, right? So if you pick infinitely many nodes, you are solving the original PDE. You are basically asking, can I satisfy my equilibrium equation for every single point? But practically speaking, you don't have to do that. Because you end up just picking a finite number of them. You just say, I want to discretize my mesh or my domain with 10 elements and 11 nodes. And then it's not going to be exact because you don't have infinitely many W functions. But maybe 10 is good enough. So I'm going to get the average error to be 0 for these 10 nodes. So that's where the flexibility of this weighted residual form comes into play, because you are picking sort of how much do you care about the error. Instead of caring about the error at every single point, you can choose. If you pick many more W's, you get better, but you can choose how much you care about the error by picking these W functions. So that is the intuition behind this weighted residual form. Calculating average error for every node. I think that is one main thing. Are there any other questions? The other thing that I would like to point out is, why do we do integration by parts? And I mentioned it last time. So why is the weak form important? The other thing that you saw in the notation that I have in this set of slides is that U and W have to be in this space called H1 or Z0. And that's related to continuity. So the original PDE, let me scroll back up here to the very, very first question. So the original PDE has a second derivative, right? If you just do the weighted residual form, that's completely equivalent to the strong form. Again, you just need to pick many W's. But because we did the extra step of doing the integration by parts, what we did is we reduced the degree of the derivative. So in the weak form, we don't have second derivatives. We have a product of first derivatives. And I mentioned this last time, that it's just much easier to build what are called C0 functions. So C0 functions are functions that are continuous, but the derivatives might be discontinuous. So you can see here, there's three types of functions that are shown here. There is this C1 function. So this one that I'm just highlighting in orange now, that's a smooth function. You can take a derivative of that and the derivative will still be continuous, right? Then C0 functions, which I'm going to highlight in blue, these are the easiest ones to interpolate. The highlight. So C0 functions are like this. They are very easy to interpolate, but they have these continuous derivatives because there's kinks. So any function that is piecewise linear has points where the derivative changes abruptly. So the function is continuous, but the derivative is discontinuous. So that means that you cannot take, because the derivative is discontinuous, then the second derivative is not defined everywhere. So that's bad. If you need to take second derivatives, you cannot use C0 functions, you need C1 functions. And then C-1 functions are discontinuous functions. So obviously that's even less continuity. So the C-1 function like here, this one has jumps. That's C-1 function. So for FE, for the original form of the PDE, we need C1. So C1 needed for the strong form, because you need to take second derivatives. Because we did integration by part, then C0, that's all you need for FE, because of the integration by part that we did. And C-1 is bad. You definitely don't want to do C-1 because you cannot even take one derivative. Yeah, so that's it. So because we did, again, the first step in the weak form, just multiplying by this weight function and integrate, is just a way to get an average error over the region W instead of caring for every single point. Then the other one thing that we get out of the weak form is that because we can do integration by parts, we can reduce the amount of derivatives that we need to take. And that means that we can interpolate the functions with less continuity requirements. So we can just ask for piecewise linear, and we can search basically for U in the piecewise linear case. Obviously, that this is another approximation, right? So if you're searching for functions in the C0 space, but the actual PDE requires a C1 function, so a function that has continuous derivatives, then you are doing an approximation. Whatever you find in C0 is not going to be your exact solution, right? So if you want to recover the exact solution, you definitely should be searching in C1. But C0 is a bigger space because it's, like I said, it's much easier to get all C0 functions are, sorry, all C1 functions are C0, right? So C0 is a big space. It's very easy to get piecewise linear functions, but any function that is C1 is part of C0 because the only thing for C0 is, can I take derivatives? So if you search for functions in C1, then you can recover your original solution, but you don't need to because of the integration by parts. You can require only C0. So this is your requirement. You don't need more than that. But obviously, if you want to recover the exact solution, then you will want to search in C1 functions, which, like I said, are a subset of C0. I think that's about it for sort of the intuition behind this weak form. These two things. One is, yeah, this average error controlled by W, and the other one is this idea of reducing the degree of continuity that you require. Yeah, something to do with integrals, that you can split the integral to integrate over the elements. And where is this going? We will introduce the discrete weak form. I kind of alluded to the fact that these W functions are associated with the nodes. And so we're going to find systematic ways in the next week of defining these weighting functions. And then because of the way these operators, like this PDE appears, we're going to be able to put it into a system of equations. I think that's about it. Yeah, so any questions? Yes, questions. In the lab report grading rubric, it says to discuss what type of elements I use and that there will be more information about this in class. What is the more information? Not for lab 1. I think that is probably more related to other labs, where not even for lab 2. So don't worry about that one. For lab 1, just the T2D2 element. But in lab 3, we already discussed things related to, how many degrees of freedom, triangular elements, quadrilateral elements, but not for lab 1 or lab 2. Any other questions? Let's stop sharing. And yeah, so if there are no other questions, then I'll let you go a little bit early. And again, lab 2 worksheet due on Friday, and also lab 1 report. And then I'll see you on Monday. Take care. Bye.